Alright, so today we're starting our new topic, which is going to be chevalley, algebras, and groups. And so we've got our same setup as always for this. Keep in mind looking at a semi-simple algebra with a Cartan subalgebra over a algebraically closed field of characters like 0. It has a root system, all that fun stuff. And so the point here is to construct our semi-simple algebra L and its irreducible representations over the integers. And there's a whole bunch of more stuff, and we're going to see about that. I don't know too much about this topic, so we'll be looking at it here. And our first topic in this chapter is the chevalley basis. Can't even spell the man's name right. Chevalley basis of L. And I am really struggling here. Sorry, 1 second. Things are always happening. Chevalley basis of L. And that's our first. And our first heading here, we're doing another triple opening is pairs of roots. Now we will prove that L has a basis for which the structured constants are integral. But here we're gonna first look at pairs of roots whose sum is also a root. Looking at we consider roots alpha and beta for which alpha plus beta is a root. With x of some alpha, x and beta, the early bracket being, of course, some element of x alpha plus beta times a structured constant of c alpha beta. Now here we have a proposition which depends only on a root system. Let alpha and beta be linearly independent roots. These are separate than my preamble there. With beta minus r alpha through beta plus q alpha, the alpha string through beta. Then, first off, the angle bracket of beta and alpha. Beta on alpha is r minus q. We've already actually proven that. This is more just a reminder. Beta. So I think this is more oriented towards a formal root system. So it's at most 2 root lengths occur in the string. I swear my writing's better than this in real life. Part C is that if their sum is a root, then the value of our r plus 1 is q times alpha plus beta on itself over beta on itself. In proof, as I said, we've already seen part A. It's more just a reminder for part B. We're going to let phi prime be the integer combos of alpha and beta inside our root system. And this is a root system of rank 2. In the subspace of E spanned by alpha and beta. If it's reducible, it must be of type A1 times A1, which we recall is just two pairs of like orthogonal roots that don't really interact at all. If it's irreducible, well, then we know phi prime is going to be, let's put it inside, is of type A2, B2, or G2 are the only root systems of rank 2. And so then you can just check by element, and you'll see that this is true. Part C, once again, can just be done by inspecting root systems of rank 2, but that's not really any fun, right? So first we note, I'm going to write this on a new line because it's long, that r plus 1 minus r cubed alpha plus beta over beta with beta, we want this to be 0. This is actually q plus 2 of beta with alpha over alpha with alpha plus 1 minus q alpha plus beta over beta squared, so we're over beta with itself, so we're essentially just expanding out that r as you would. Then from here it's mostly just like algebra. We bring our 2 beta comma alpha over alpha comma alpha to the front, plus 1 minus q of alpha beta and beta minus 2q of alpha with beta over beta with beta. This is just having our 2q terms kind of bounce off each other. And the point is that we can then factor this into the angle bracket of beta with alpha plus 1 with 1 minus the q of alpha and alpha over beta and beta. And so we're going to call this a, we call this B. And for this to be 0, obviously one of these has to be 0. And so because alpha and beta are not symmetric, we have to split this into cases. So case 1 is where alpha is bigger than, or the size of alpha is bigger than the size of beta, or equal. Well, then the size of the angle bracket of beta on alpha is less than the size of the angle bracket of alpha on beta. And since alpha and beta are independent, we know that the angle bracket of beta times alpha with alpha times beta is 0, 1, 2, or 3, as we saw before. By the inequality, the angle bracket of beta on alpha is minus 1, 0, or 1. In If, in the first case, which the angle bracket of beta and alpha is -1, a equals 0, and we're done. Otherwise, the angle bracket of beta and alpha, otherwise the curved bracket, I don't know why I wanted to call it a soft bracket of beta and alpha, is non-negative. So beta plus alpha is strictly larger than both of beta with itself and alpha with itself. Since alpha plus beta is in a root system, we know there's only 2 root sizes. So alpha and beta have to both be small roots, while beta plus alpha is then a big root. And similarly, we have that beta plus 2 alpha, the size of beta plus 2 alpha is bigger than the size of beta and alpha. But beta plus alpha is a big root. So beta plus 2 alpha can't actually be a root. So Q is 1 and B is 0. Yeah. And the second case is where alpha is strictly less than beta, because our above case covered equality too. So in this case, well, the size of alpha plus beta is either the size of alpha or the size of beta by part B. So either way, we have that size of alpha, the soft bracket of alpha and beta, the curved bracket, and why I keep saying soft, is negative. So the angle bracket of alpha and beta is negative. Thus, the curved bracket of beta minus alpha is greater than beta, is greater than alpha, but keep in mind we only have 2 sizes, and beta and alpha are both roots, so beta minus alpha is not a root. So R is 0. Again, the product of alpha on beta and beta on alpha is an integer between 0 and 3. And here we have that the size of alpha on beta is less than the size of the angle bracket of beta on alpha. So this time the angle bracket of alpha on beta is -1, 0, or 1. As the angle bracket of alpha and beta has to be negative though, it must be -1. So Q is negative of the angle bracket of beta on alpha, which is the angle bracket of beta on alpha over the angle bracket of alpha over beta, which is the curved bracket of beta on beta, over the curved bracket of alpha on alpha. So b is just 0. Alright, this brings us on to the existence of a chevalley basis. Of a chevalley basis. And so our lemma, we're going to start out here. We're going to once again have alpha and beta be independent roots. We're going to choose an x alpha in L alpha, an x beta in L beta. I mean, no, I did not even read. Choose an x negative alpha in L negative 8 alpha, for which the Lie bracket of x alpha and x negative alpha is h of alpha. And we're going to let x beta be an L beta with no real restrictions. Then if beta minus RA through beta plus QA alpha is the alpha string through B, through beta, then the bracket of x negative alpha, bracket of x negative alpha on the bracket of x alpha and x beta is q times r plus 1 times x beta. And the proof, if alpha plus beta is not a root, then I didn't write the word f, then q is 0, and the bracket of x alpha and x beta is 0, so our equation is 0 on both sides. Now for our general case, we're going to, of course, work with the adjoint representation of S alpha, which we remember is isomorphic to the two-dimensional, the rank 2 special linear Lie algebra on F. So we see that the S alpha submodule of L generated by x beta has dimension r plus q plus 1, which is the number of roots in the alpha string through B, and highest weight r plus q. In the notation of the above, we see that x beta is a non-zero multiple of VQ, and the successive application of the adjoint of x alpha and the adjoint of x of negative alpha multiplies VQ by the scalar QR plus 1. Let's prove our lemma. So let's go on to a proposition. Which says that we can choose root vectors x alpha in L alpha for alpha in anywhere in our root system, such that, first off, the angle bracket of x alpha and x negative alpha is h alpha, that is, and b, if alpha and beta are roots such that their sum is also a root, then the Lie bracket of x alpha on x beta is our x alpha plus beta times a structure coefficient c alpha beta, and then c alpha beta is negative c of negative alpha and negative beta for any such choice, for any choice of root vectors the set of scalars c alpha beta for, of course, alpha, beta, alpha plus beta being in our root system satisfy our third condition, which states that c squared of alpha and beta is q times r plus 1 times the size of alpha plus beta over the size of beta where beta minus r alpha through beta plus q alpha is, of course, our alpha string through beta. I'm just going to write it as a string because you can tell which root is going through what based on this series. Alright, so let's look at our proof. Recall that L has an automorphism sigma of order 2 sending L alpha to L negative alpha and acting on H by multiplying by negative 1 for arbitrary non-zero x alpha and L alpha, letting x negative alpha be negative sigma of x alpha, which is of course going to be in L negative alpha, is non-zero. And the killing form of x alpha and x negative alpha is non-zero. Scaling x alpha by c, by some c and f, multiplies this value by c squared. Since we're assuming our base field is algebraically closed, we can make k the killing form of x alpha and x negative alpha take any non-zero value. We're going to specify here that the killing form of x alpha and x negative alpha is 2 over the size of alpha. by a previous proposition. This forces the bracket of x alpha and x negative alpha to be h alpha, which you recall is 2t alpha over the size of alpha plus alpha, the form of alpha with alpha. So for each pair of roots, alpha and negative alpha, we fix such a choice. Which gives us which just wants the bracket of x alpha and x negative alpha to be h alpha. Now we need to show that our scaling factors behave in the way we want them to. So now we're going to let alpha and beta be summable roots in our root system. So x alpha formed with x beta is going to be some multiple scaled by a factor of c alpha beta of x alpha plus beta. For c alpha beta, they don't only write it with the comma, I did it by accident, is f. Alright, new page already. Applying our sigma, we get the bracket of negative x negative alpha with negative x negative beta is negative c alpha beta on x of negative alpha negative beta as the bracket of x negative alpha and x negative beta is equal to c negative alpha negative beta times x of minus alpha minus beta. We get condition B. Now, having chosen our root vectors for a and b, with alpha, beta being roots, with their sum being a root, we can move on to our third condition. Since t of alpha plus beta is t of alpha plus t of beta, let's just clean that up. We get that c alpha beta of x alpha plus beta with c alpha beta x negative alpha negative beta is c squared alpha beta h alpha plus beta. Once again, I was overconfident and should have done some new line, which is 2c squared alpha beta over alpha plus beta times t alpha plus t beta. We also get that the left-hand side equals negative of the bracket of x alpha of x beta with the bracket of x negative alpha, x negative beta, which is equal to negative of x alpha on x of beta on x alpha x beta. I'm just going to write this on a new line. I'll rewrite this all. So we have this, which I already went through before. is equal to negative x alpha on x beta on x negative alpha plus, x negative alpha with x negative beta plus x beta with x alpha with x negative alpha on x negative beta. Which we can just flip around these inside terms. We can flip some terms around by anti-symmetry to get x alpha on x beta on x negative beta with x negative alpha plus x beta on x alpha on x negative alpha, x negative beta. Now let the beta string through alpha be alpha minus r prime beta through alpha plus q prime beta. Then we apply the lemma, the previous lemma, to each term after inverting alpha and beta to the negatives to get q prime of r prime plus 1 times the bracket of x alpha, x negative alpha, plus q times r plus 1 times x beta with x negative beta, which is equal to 2 times q prime times r prime plus 1 over the size of alpha with itself on t alpha plus 2q r plus 1 on the size of beta with itself times t beta, and comparing those coefficients with the above and by the linear independence of t alpha and beta, this gives us part C. From this, we may now construct a chevalley basis of L, which is the basis of x alpha across our roots and hi, whereas I ranges from 1 to our rank L, for which the x alpha satisfy, they say alpha A and B is the above. C is just stating a property, so we'll just say it's satisfy the above, and hi equal h alpha I for some base delta being alpha 1 through alpha L of phi. And this leads us to a theorem by Chevalley we're going to let our collection of x alpha across a root system and hi from 1 through L be the chevalley basis of L. And then the structure constants line Z in our their integers, and more precisely first off for alpha, the bracket of hi and hj is 0. The bracket of hi with x alpha, the angle bracket of alpha with alpha I times x alpha. Part C is that x alpha, x negative alpha is what we're going to call h alpha, which is a integer linear combination of hi from 1 to L. And part D is that if alpha and beta are independent roots, with string of beta minus r alpha through beta plus q alpha, then the Lie bracket of x alpha and x beta is 0 if q is 0, so if b plus alpha is not a root, and x alpha, Lie bracket of x alpha and x beta is plus or minus r plus 1 times x alpha plus beta if, on the other hand, q is at least 1, which gives us that alpha plus beta is a root. The proof we already have, once again, we already have A. We get part B by the fact that alpha of hi is just alpha with alpha I. So that one is also immediate. For part C, recall that the dual roots 2 alpha over alpha alpha form a root system with a base on horizontally lined being our delta dual, being the collection of alpha dual I from 1 to L under the killing form identification of H with H star. T alpha corresponds to alpha, and H alpha to the dual of alpha. Since each alpha dual is an integer linear combination of elements of our dual basis, each H alpha is an integer linear combination of the hi from 1 to L. And this also gives D by adding previous results. Now, it says here that the fact that C of alpha beta is negative C of negative alpha and negative beta, and not C of negative alpha and negative beta, may seem strange, but note by A and the Jacobi identity, C alpha beta times C negative alpha negative beta is equal to minus R plus 1 squared which means that part B, part D requires part B. Reminder of what those are here. And you can verify that you can get chevalley bases for the classical algebras. That's our family of A, B, C, and D, which are the special linearly algebra, the even and odd dimensional orthogonal Lie algebras, and the symplectic Lie algebras. And so Chevalley's theorem has the virtue of providing a uniform existence proof for Chevalley bases and specifying how the structure constants actually arise from such a basis, and that appears to be our video. Next time we will be looking at uniqueness of the Chevalley bases, and then we'll be moving on to reduction modulo primes and constructing Chevalley groups and all sorts of scary stuff. So look forward to that next time, I guess. Thanks for watching.